Picture holding a teaspoon filled with something so impossibly heavy, it would crush entire mountains under its weight. Now imagine that same object whirling through space faster than a kitchen blender at full speed. This isn't science fiction. This is the reality of neutron stars, the universe's ultimate cosmic powerhouses. These remnants of dead stars pack more mass than our sun into a sphere no wider than a city, creating gravitational forces so intense they warp the very fabric of space-time. But what's even more astonishing, some of these stellar corpses spin hundreds of times every single second, defying everything we thought we knew about the laws of physics. How can something so unimaginably dense move so fast without tearing itself apart? The answer lies in a dance between quantum mechanics and gravity so bizarre, it rewrites the rules of the cosmos. Think about the last time you spun a stopwatch as it wobbles, slows, and eventually stops. Now erase that intuition completely. Neutron stars don't play by those rules. Their spins are locked in a battle between crushing gravity and the strange subatomic forces bubbling beneath their surfaces. Inside these stars, matter isn't just squeezed, it's transformed. Protons and electrons fuse into a swirling ocean of neutrons, creating a quantum playground where particles behave in ways that would make even Einstein pause. And when these stars rotate, they don't just spin, they whip space itself into a frenzy, sending out gravitational waves that ripple across the universe. So why does any of this matter to us? Because neutron stars are cosmic laboratories, testing the limits of physics in ways we could never replicate on Earth. Their spins hold clues to some of the biggest mysteries out there, from the nature of dark matter to the origins of heavy elements like gold and platinum. Every flicker, every wobble in their rotation is a message, a piece of a puzzle written in the language of quantum mechanics and relativity. And today, we're going to decode that message together. Strap in, we're about to dive into one of the most extreme phenomena in the universe, where the rules of the very small meet the forces of the unimaginably large. By the end, you'll never look at the night sky the same way again. To grasp the incredible spin of neutron stars, we need to rewind to their violent birth, a moment when the laws of physics are pushed to the breaking point. Picture a star at least 8 times more massive than our sun, burning through its fuel over millions of years. As it runs out of nuclear fuel, the outward pressure that once held it up vanishes, and gravity takes over in a catastrophic collapse. In less than a second, the star's core, a region the size of a city, implodes with such force that it rebounds in a titanic explosion known as a supernova. This cosmic detonation blasts the star's outer layers into space, leaving behind only its crushed heart, a neutron star. But here's where things get truly strange. During that collapse, the core doesn't just shrink, it undergoes a radical transformation. The immense pressure forces protons and electrons to merge, creating a sea of neutrons so densely packed that a single sugar cube's worth would weigh as much as a mountain. And just like a figure skater pulling in their arms to spin faster, this collapsing core speeds up dramatically. A star that might have rotated once every few weeks in its prime now spins hundreds of times per second, its rotation amplified by the same physics that sends a pirouetting ice skater into a dizzying whirl. This isn't just a quirk of nature, it's a cosmic balancing act. The newborn neutron star's spin is a direct result of the conservation of angular momentum, a fundamental law that keeps the universe's rotations in check. But unlike a skater who eventually slows due to friction, neutron stars have almost nothing to stop them. With no air resistance in space and a structure so rigid it could withstand forces strong enough to shatter planets, these stellar remnants can maintain their dizzying spins for millions of years. Yet some neutron stars don't just spin, they accelerate. How? That's where the real mystery begins. The difference between how a neutron star spins and how, say, a planet rotates is like comparing a whirlpool to a single drop of water. They may seem similar at first glance, but the forces at work couldn't be more different. Take a spinning basketball. Its rotation comes from the physical motion of its mass, with speed depending on how hard you throw it and how its weight is distributed. But a neutron star's spin isn't just about motion, it's woven into the very fabric of its existence. At the subatomic level, particles like electrons and quarks possess something called quantum spin, a fundamental property as intrinsic as their charge or mass. This isn't spin in the traditional sense. Particles aren't actually whirling like tiny tops. Instead, it's a quirky feature of quantum mechanics that gives particles a kind of built-in angular momentum, even when they're perfectly still. Now scale that up to a neutron star. Here, trillions upon trillions of neutrons, each with their own quantum spin, are crammed together so tightly that their individual spins begin to interact, creating a collective rotation that defies classical physics. Unlike a basketball slowing down due to air resistance or friction, a neutron star's spin is anchored in these quantum rules, making it eerily stable. That's why some of these stars can maintain spins of hundreds of rotations per second for millennia, with barely any slowdown. But the real magic happens when quantum spin meets gravity's extreme pull. The star's crust, a crystalline layer just a kilometer thick, is under such immense strain that it occasionally cracks, causing sudden jumps in rotation called glitches. These aren't just random hiccups, they're cosmic messages, revealing how quantum behavior plays out on a scale larger than anything in our labs. What makes this duality so fascinating is how it blurs the line between the tiny and the enormous. In most of the universe, quantum effects are too subtle to notice at large scales, drowned out by the predictable rules of classical physics. But inside a neutron star, gravity amplifies these quantum quirks until they dominate the star's very behavior. It's as if you took the strange rules of a subatomic particle and inflated them to the size of Manhattan, creating a celestial object that spins not because it's being pushed, but because spinning is simply part of its nature. This is why astrophysicists treat neutron stars as Rosetta Stones. They're the only places in the cosmos where quantum mechanics and gravity collide so dramatically, offering us a front-row seat to physics we can't recreate anywhere else. Among the most mesmerizing spin artists in the cosmos are pulsars, neutron stars that don't just rotate, but announce their presence to the universe with rhythmic flashes of light. Imagine a lighthouse on a galactic scale, its beam slicing through the darkness with such precision you could set your watch by it. These celestial beacons emit focused jets of radiation, often radio waves, but sometimes X-rays or gamma rays, that sweep across space like the beam of a cosmic searchlight. Every time that beam points toward Earth, we detect a pulse, some flashing dozens or even hundreds of times per second, with a regularity that rivals the most accurate atomic clocks ever built. What keeps these cosmic timekeepers so astonishingly steady? The secret lies in their mind-bending density. A pulsar's rotation is anchored by its unimaginable mass, packed into such a small volume that it becomes almost impervious to outside forces. Like a spinning top made of solid diamond in a frictionless void, once set in motion, it resists slowing down. But pulsars take this stability to extremes. Their magnetic fields, trillions of times stronger than Earth's, act like cosmic guide rails, channeling energy into those precise beams and keeping the star's spin unnervingly consistent. Some pulsars, like the famous one at the heart of the Crab Nebula, have maintained their rhythm for centuries with deviations measured in mere billionths of a second. Yet even these paragons of cosmic regularity sometimes stumble. Occasionally, a pulsar's spin will suddenly speed up in what scientists call a glitch, a split-second hiccup where the star's rotation jumps by a tiny but measurable fraction. These glitches are like cosmic earthquakes, likely caused by cracks in the neutron star's ultra-dense crust or sudden shifts in the superfluid ocean of neutrons swirling beneath its surface. Then there are the opposite events called anti-glitches, where the star mysteriously slows down without warning. Each of these events sends astrophysicists scrambling for explanations, offering glimpses into the bizarre physics at work inside these stellar remnants. The real magic of pulsars isn't just in their precision, it's in how we've learned to use them. Because their pulses arrive with such predictable timing, astronomers have turned them into tools for testing Einstein's theory of relativity, mapping the Milky Way's magnetic fields, and even searching for gravitational waves. In one famous experiment, observations of a pulsar orbiting another neutron star provided the first indirect evidence of gravitational waves, earning the researchers a Nobel Prize. And because pulsars slow down at predictable rates over millennia, their spin rates act like cosmic clocks, letting us measure astronomical timescales with incredible accuracy. But perhaps the most tantalizing question about pulsars is what happens when they finally run down. As these spinning giants gradually lose energy, their pulses grow fainter and farther apart. Some will spin quietly into oblivion, while others may transform into even stranger objects like magnetars, neutron stars with magnetic fields so strong they could strip the information from a credit card halfway across the solar system. Every flicker, every glitch, every gradual slowdown is a chapter in a story written in the language of physics, one we're only just beginning to translate. And with every pulse detected, we're reminded that these distant, spinning relics are more than just cosmic curiosities, they're masterpieces of nature's precision engineering. If neutron stars are the universe's spinning tops, then millisecond pulsars are the cosmic equivalents of turbocharged engines, revving up to speeds that would make even the fastest race cars look sluggish. These extreme objects whip around hundreds of times every second, their surfaces moving at a significant fraction of the speed of light. How does something with the mass of a star packed into a space no bigger than a city reach such dizzying velocities? The answer lies in a celestial tango between two stars, a dance of matter and gravity that transforms an already extraordinary object into one of the fastest spinning things in the known universe. Most millisecond pulsars weren't born spinning this fast, they were given a cosmic push. Imagine a neutron star locked in orbit with a companion star, slowly siphoning off gas from its neighbor. As this stolen matter spirals inward, it doesn't just disappear, it carries with it something crucial, angular momentum. Like a figure skater catching weights mid-spin and pulling them inward, the neutron star gains rotational energy with every drop of material it absorbs. Over hundreds of millions of years, this steady diet of stellar matter can accelerate the pulsar from a modest spin of a few rotations per second to a blistering several hundred. The result, a millisecond pulsar, a stellar remnant spinning so fast that if it were any larger, the centrifugal force would tear it apart. But here's where the physics gets truly mind-bending. At these speeds, the surface of a millisecond pulsar is moving at roughly 15% the speed of light. That means if you could stand on its surface, an impossible feat given the crushing gravity, you'd be hurled into space by sheer rotational force long before you even had a chance to blink. The star's intense gravity barely manages to hold it together, creating conditions where the laws of general relativity and quantum mechanics collide in ways we're still struggling to understand. What's even more astonishing is how these speed demons serve as natural laboratories for testing the extremes of physics. Their precise pulses act like cosmic clocks, allowing scientists to probe the nature of spacetime itself. Some millisecond pulsars are so stable that their timing can detect gravitational waves passing through our galaxy, ripples in space caused by distant collisions of black holes. Others orbit other neutron stars or white dwarfs in such tight, fast loops that they provide the most stringent tests of Einstein's theory of general relativity ever conducted. Yet for all their precision, millisecond pulsars still hold mysteries. Some spin faster than current models predict they should, suggesting there might be unknown processes at work in their cores. Others show sudden, tiny changes in their rotation rates, hinting at quantum phenomena unfolding deep within their interiors. And then there are the Black Widow pulsars, millisecond pulsars that have nearly evaporated their companion stars with their intense radiation, leaving behind only a wisp of what was once a star. These cosmic speedsters remind us that the universe is far stranger and more dynamic than we often assume. They push the boundaries of what we thought was possible, forcing us to rethink how matter behaves under conditions so extreme they defy imagination. And with every new millisecond pulsar discovered, we're given another piece of the puzzle, another clue in understanding not just these incredible objects, but the fundamental laws that govern everything from the smallest particles to the largest structures in the cosmos. Even the most precise cosmic clocks sometimes stutter. For neutron stars, these sudden hiccups called glitches are more than just irregularities. They're explosive windows into the hidden physics raging beneath their surfaces. Picture a starquake, the neutron star's crust, a rigid lattice of atomic nuclei under unimaginable pressure, suddenly cracks like a frozen lake in winter. This fracture releases built-up stress, causing the entire star to jolt forward in its spin, sometimes gaining an extra few rotations in mere seconds. But crust fractures alone can't explain the most dramatic glitches. Some of these stars speed up by fractions of a second so abruptly, it's as if someone slammed the accelerator on a spinning carousel. The real secret lies deeper, in a layer of the neutron star where physics defies everyday intuition. Beneath the crust, neutrons aren't locked in place, they flow in a frictionless quantum superfluid, a state where particles move with zero resistance. Normally, this superfluid rotates in sync with the star's crust, bound by the star's immense magnetic field. But as the crust gradually slows due to energy loss from radiation, the superfluid, untouched by friction, spins faster, storing energy like a wound-up spring. When the difference becomes too great, the superfluid suddenly transfers its pent-up momentum to the crust in a violent surge, kicking the star's rotation into overdrive. These events aren't just curiosities, they're cosmic diagnostics. Each glitch leaves fingerprints revealing the star's internal structure. Smaller, frequent jumps hint at a rigid crust with shallow fractures, while rare, massive speed-ups suggest a deeper superfluid layer detaching like an unstoppable current beneath ice. Some glitches even come with aftereffects, a gradual relaxation period where the star's spin slowly adjusts, as if catching its breath after a sprint. But the surprises don't end there. A handful of neutron stars do the opposite. They suddenly slow down in what scientists call an anti-glitch. These backward stumbles might occur when the star's magnetic field, tangled like spaghetti in a whirlpool, suddenly reorganizes itself, applying an electromagnetic brake to the crust. Or perhaps pockets of the superfluid briefly decouple, stealing rotational energy instead of donating it. Either way, these exceptions prove that neutron stars are far from simple spinning tops. They're dynamic, layered worlds where quantum weirdness plays out on a cosmic scale. What makes glitches truly invaluable is how they turn neutron stars into natural laboratories. By timing these spin changes with radio telescopes, researchers can map interiors we'll never physically reach, testing theories about how matter behaves at densities trillions of times greater than steel. Some models suggest the cores of these stars might contain exotic particles like hyperons or free quarks, states of matter that could rewrite our understanding of nuclear physics. Every glitch, every tiny deviation in rotation, is a message bottled in space-time waiting to be decoded. And with each one we decipher, we move closer to answering one of astrophysics' biggest questions. What happens to matter when gravity wins its ultimate victory over the atomic world? Beneath the crushing weight of a neutron star's crust, something extraordinary is happening. A swirling ocean of neutrons isn't just sitting still, it's moving with perfect, frictionless precision. This isn't ordinary matter, it's a superfluid, a state so bizarre it defies everything we know about how liquids behave. Imagine pouring a cup of water that never slows down, never loses energy, and whirls forever without a single drop of resistance. That's the reality inside a neutron star's core, where quantum mechanics takes the reins and rewrites the rules of motion. What makes this superfluid so strange? At temperatures just above absolute zero, something the neutron star's core achieves naturally under its own immense density. Neutrons pair up and begin flowing without any viscosity. It's like an infinite cosmic slinky cascading down a staircase with no energy loss forever. But here's the twist. This superfluid doesn't just passively exist, it dances to its own rhythm. While the star's solid crust rotates at one speed, the superfluid beneath can spin independently, like a gyroscope inside a spinning top. This mismatch creates a ticking time bomb of stored energy, waiting to be unleashed in the form of glitches or even stranger phenomena. The real magic happens when these two layers interact. Think of it as a cosmic tug of war. The crust, slowed by magnetic braking and radiation, gradually loses rotational energy. But the superfluid, oblivious to friction, keeps spinning at its original pace. Over time, the difference builds until snap. The superfluid suddenly transfers its pent-up momentum to the crust in a violent surge. It's as if the star's own interior has a mind of its own, kicking the brakes or slamming the accelerator without warning. But the implications go far beyond spin changes. This internal frictionless flow may also be responsible for some of the most powerful magnetic fields in the universe. As the superfluid churns, it could generate colossal currents, amplifying the star's already unimaginable magnetism into something even more extreme, like the fields seen in magnetars, which are strong enough to distort atoms into needle-thin shapes from thousands of kilometers away. And then there's the ultimate mystery. What happens at the very center? Some theories suggest the core might not even be made of neutrons at all, but a soup of free quarks or other exotic particles, all flowing in perfect quantum harmony. If true, this would mean neutron stars aren't just dead stellar remnants, they're active, evolving laboratories where matter exists in states we can't replicate anywhere else in the cosmos. Every glitch, every slowdown, every magnetic flare from these stars is a clue. By studying them, we're not just learning about distant objects, we're peering into the quantum heart of the universe itself, where the rules of the infinitesimal meet the forces of the infinite. And with each discovery, we get closer to answering one of physics' biggest questions. What happens when matter is pushed to its absolute limit? The same magnetic fields that give neutron stars their cosmic lighthouse beams also act as invisible brakes, slowly sapping their spin over millennia. These aren't just ordinary magnetic forces, they're monsters, billions of times stronger than Earth's, capable of wrenching electrons from atoms light years away. Like a spinning top immersed in molasses, the star's rotation gradually slows as its magnetic field plows through the surrounding nebula, transferring energy to stray particles in a process called magnetic braking. But here's the twist. Sometimes these fields don't just slow the star down, they can also become cosmic catapults, flinging material outward with such force that they actually speed up the star's spin in a celestial paradox. Take the case of a neutron star accreting matter from a companion. As gas spirals onto its surface, it doesn't just add mass, it brings angular momentum, like a steady hand nudging a merry-go-round. But the star's magnetic field can disrupt this flow, channeling material toward its poles in fiery columns. If the field is strong enough, it might fling some of this material clear off the star's equator, carrying away angular momentum and paradoxically slowing the spin. Yet in other systems, the field lines can become so twisted they act like elastic bands, storing rotational energy before snapping back and giving the star a sudden speed boost. The real enigma lies in Magnetar's neutron stars with magnetic fields 1,000 times stronger than average. These fields are so intense they can crack the star's crust in Starquakes, releasing bursts of energy that alter its spin unpredictably. One moment, the star might slow down as its field drags against interstellar plasma. The next, a magnetic reconnection event could inject fresh momentum, like a cosmic slingshot effect. It's a turbulent dance where the rules change by the second, and astronomers are still piecing together why some neutron stars break hard while others get occasional kicks forward. What makes this magnetic interplay so crucial is how it shapes the star's lifespan. A young, highly magnetic neutron star might slow to a crawl within tens of thousands of years, its brilliant pulses fading into obscurity. Meanwhile, a millisecond pulsar with a weaker field can maintain its blistering spin for billions of years, outliving entire galaxies. These braking mechanisms don't just affect the star, they ripple across the cosmos, influencing how neutron stars distribute heavy elements, energize nebulae, and even signal their presence to distant observers. Every slowdown, every unexpected speed bump, is a clue written in magnetic ink, waiting to reveal how the universe manages its most extreme rotational forces. Einstein's theory of general relativity isn't just abstract math, it comes alive in the extreme gravity of a spinning neutron star, where space and time twist into knots. Imagine throwing a bowling ball onto a trampoline. The indentation it creates is like the warping of space by mass. But if that ball starts spinning, it doesn't just dent the fabric, it drags it around in a swirling motion. That's frame dragging, a real-world effect where a rotating neutron star doesn't just sit in space-time. It pulls the very fabric of the universe along with it like a cosmic whirlpool. The numbers here are staggering. Near a neutron star's surface, frame dragging can twist space-time so severely that an object orbiting close by would be yanked sideways, its path bent not just by gravity but by the star's spin. Picture a satellite circling Earth, but instead of following a predictable ellipse, it's tugged into a corkscrew trajectory by the planet's rotation, except with a neutron star. This effect is billions of times stronger. Even light isn't immune. Photons skimming past the star's poles get their polarization twisted, a phenomenon called the lens-thirring effect, leaving detectable fingerprints in the star's radiation. What makes neutron stars ideal for testing this relativity in action is their combination of extreme density and blistering spin. A star like PSRJ 1748-2446 AD, spinning over 700 times per second, doesn't just warp space-time, it churns it into a vortex so intense that time itself flows differently near its surface. Clocks at its poles would tick measurably slower than those at its equator due to this rotational time dilation. a prediction of relativity that's been confirmed with mind-bending precision. But the real magic happens in binary systems where two neutron stars orbit each other. As they spiral inward, their mutual frame dragging creates intricate spacetime ripples, like two spinning tops woven together by invisible threads. These interactions are so precise that they've allowed astronomers to measure frame dragging indirectly through tiny shifts in the star's orbits, confirming Einstein's predictions to within a fraction of a percent. Yet some mysteries remain. Frame dragging might explain why certain neutron stars exhibit sudden torque reversals, where their spin rates mysteriously fluctuate. One theory suggests that misaligned magnetic fields, wrestling with the star's dragged spacetime, could periodically transfer angular momentum between the crust and the superfluid core. Others propose that frame dragging itself could amplify magnetic reconnection events, unleashing bursts of energy that nudge the star's rotation. These aren't just academic curiosities, they're clues to how spacetime behaves under conditions so extreme they border on the surreal. Every pulse from a neutron star, every wobble in its spin, carries encrypted messages about the universe's deepest workings. And as our telescopes grow sharper, we're learning to read them, one relativistic twist at a time. Even the smoothest-looking neutron star hides tiny imperfections, cosmic mountains no taller than a few millimeters, yet dense enough to warp spacetime itself. These minuscule bumps, formed by the star's crushing gravity or fractures in its crystalline crust, create a peculiar kind of asymmetry. As the star spins, these mountains don't just disturb the surface, they send ripples through the very fabric of the universe, generating gravitational waves that travel across light years. Unlike the violent collisions between black holes that LIGO typically detects, these waves are subtler, a continuous hum in the cosmic background, like the steady drone of a cello string beneath a symphony. Why does this matter? Because these waves carry encoded details about the star's structure that light alone can't reveal. By measuring the frequency and amplitude of these ripples, scientists can deduce how fast the star is spinning, how much it's deformed, and even what's happening beneath its surface. It's like listening to a bell's ring to determine if it's cracked, except in this case, the bell is a city-sized object spinning faster than a blender blade, and the sound vibrates through spacetime itself. Some neutron stars, like the hypothetical Gravitors, might emit gravitational waves so steadily that future observatories could track them for years, watching for minute changes that hint at internal quark soup or cracks in their superfluid cores. The real breakthrough will come when we detect gravitational waves from isolated neutron stars, ones not pulsing with radio beams or locked in binary systems. These silent spinners, invisible to traditional telescopes, could outnumber pulsars 10 to 1, hiding in plain sight until gravitational wave astronomy pulls back the curtain. Already, projects like LISA and the Einstein telescope are being designed to catch these whispers from the void. And if they succeed, we might finally solve mysteries like why some neutron stars glitch while others don't, or whether their cores contain free quarks or other exotic particles. But the most tantalizing possibility is this: gravitational waves could reveal neutron stars we never knew existed, ones spinning so fast they're on the verge of tearing apart, or so dense they've crossed the threshold into quark stars. Each ripple they emit is a breadcrumb trail leading us closer to understanding matter's ultimate limits. And as our detectors grow more sensitive, we're not just listening to the universe's soundtrack, we're learning to read the sheet music, one space-time vibration at a time. When two neutron stars finally spiral into each other after billions of years in a slow cosmic dance, their collision isn't just a merger, it's a spin-powered apocalypse. Picture two city-sized objects, each weighing more than our sun, smashing together at nearly the speed of light. The energy released in that instant outshines entire galaxies, but what happens next depends on a delicate balance between gravity and rotation. If their combined angular momentum is too great, the collision creates a hypermassive neutron star, a temporary, unstable monster spinning so fast it flirts with disintegration. For a few fleeting milliseconds, this remnant wobbles violently, its surface rippling like a water balloon squeezed too hard before gravity finally wins and it collapses into a black hole. But angular momentum doesn't just decide the fate of the remnant, it shapes the entire explosion. As the stars tear each other apart, their spinning outer layers fling debris into space at relativistic speeds, forming jets of material that glow with the heat of a trillion suns. These jets aren't just random ejections, they're sculpted by the same rotational forces that once kept the stars intact. The debris field becomes a cosmic crucible, where neutrons ram into atomic nuclei with enough force to forge heavy elements like gold, platinum, and uranium. In fact, a single neutron star merger can produce more gold than all the mines on Earth combined, enough to lasso entire planets with solid gold chains. What's truly mind-bending is how these collisions serve as cosmic spin laboratories. When astronomers detected the first neutron star merger in 2017, they didn't just see a flash of light, they caught the gravitational wave signature of two objects spiraling faster and faster as they neared collision. The data revealed how their mutual orbit tightened from 30 times per second to nearly 1,000 in the final moments, a death spiral so rapid it warped spacetime like a blender set to cosmic puree. And in the aftermath, the hypermassive remnant's spin left fingerprints in the gamma-ray burst that followed, its flickering light curve hinting at a central engine whirling at near breakup speed. Yet mysteries remain. Some mergers produce unexpectedly bright explosions, suggesting hidden factors like magnetic field amplification or shockwave interactions might be stealing rotational energy and repurposing it as light. Others leave behind magnetars, neutron stars with magnetic fields so strong they could power the explosion for years. And then there's the question of what happens to angular momentum when the remnant finally collapses. Does it vanish into the black hole singularity, or is it somehow ejected in those luminous jets? Every merger we observe is a Rosetta Stone for extreme physics, revealing how rotation governs the universe's most violent events. As gravitational wave detectors grow more sensitive, we're on the verge of catching dozens of these cosmic spin battles each year, each one a chance to decode how the universe builds its heaviest elements, powers its brightest explosions, and recycles the angular momentum of dead stars into new celestial wonders. The gold in your jewelry might be stardust, but its origin story is written in the whirl of colliding neutron stars, a reminder that even in destruction, the cosmos never stops spinning. Every cosmic spinner has its breaking point, even a neutron star. Just as a washing machine shakes violently if unbalanced at high speeds, these ultra-dense objects can only whirl so fast before centrifugal forces overpower gravity's grip. The key to this speed limit lies in a number every astrophysicist knows: the Chundrescar Limit, the maximum mass a stable neutron star can sustain before collapsing into a black hole. But mass isn't the only factor. Rotation plays a starring role in this balancing act. Push a neutron star's spin too close to 1,000 rotations per second, and the outward force from its motion begins to rival the inward pull of its own gravity, stretching the star into an increasingly oblong shape. At the breaking point, even a tiny nudge like matter accreting from a companion star could trigger an explosion or collapse. The fastest known pulsar, PSRJ 1748-2446 AD, skirts this edge at 716 revolutions per second, so rapid its equator moves at roughly a quarter the speed of light. At this velocity, the star's surface experiences time dilation so extreme that an hour there could equal years elsewhere in the galaxy. Yet theoretical models suggest neutron stars could spin even faster under ideal conditions, perhaps up to 1,500 rotations per second, if born from the merger of two lighter neutron stars. These hypothetical, supramassive neutron stars would be temporary cosmic acrobats, their immense angular momentum postponing gravitational collapse for minutes or months before succumbing. But here's where quantum physics throws a curveball. As the star spins faster, relativistic effects cause its internal structure to change. The superfluid core, normally frictionless, develops vortices that sap energy, while the crust's crystalline lattice warps under strain, triggering frequent starquakes. Some simulations predict that near the spin limit, the star's equator could bulge so dramatically that it forms a disk of ejected material, a cosmic smoke signal marking its impending demise. The real mystery: some neutron stars seem to defy these predictions. X-ray observations have revealed objects like JRO-J 1744-28, where bursts of material temporarily accelerate the star beyond expected stability thresholds, only to see it recover mysteriously intact. Others, like the Black Widow pulsars, appear to balance precariously at their spin limits for millennia, flirting with disintegration yet somehow holding together. These outliers suggest there's still much we don't understand about how neutron stars manage their angular momentum, whether through hidden energy sinks in their cores or magnetic fields acting as cosmic shock absorbers. What makes these speed limits so fascinating isn't just the physics, it's how they shape the universe. A neutron star spinning at its maximum rate becomes a gravitational wave powerhouse, emitting ripples in spacetime so strong they could be detected across intergalactic distances. And when one finally crosses the threshold and ruptures, the explosion could seed nearby nebulae with rare elements forged in its final moments. Every millisecond of a neutron star's spin is a battle between creation and destruction, where the universe's strictest speed laws decide whether it lives as a cosmic beacon or dies in a flash of relativistic fire. Deep within the turbulent heart of a neutron star's superfluid core, physics takes a sharp turn into the bizarre, where swirling rivers of neutrons don't just flow, but twist into microscopic whirlpools called quantum vortices. Picture a bathtub drain sucking water into a spiral, except here, the water is a frictionless quantum sea, and each whirlpool is thinner than an atom yet stretches from the star's core to its crust. These aren't mere eddies, they're cosmic conveyor belts for angular momentum, each one a tiny tornado spinning with mathematical precision, their rotation quantized so strictly that they can only whirl at specific, discrete speeds. What makes these vortices so extraordinary is how they bridge quantum weirdness with stellar-scale forces. In most fluids, vortices jumble chaotically, colliding and dissipating like smoke rings in a breeze. But in a neutron star's superfluid, quantum rules enforce perfect order. Vortices arrange themselves into hexagonal lattices, like the atoms in a crystal, but constantly in motion. As the star rotates, these vortices migrate outward, carrying rotational energy from the faster spinning core to the slower crust. It's as if the star's spin isn't governed by solid mechanics, but by an intricate quantum ballet where every dancer knows their steps perfectly. The real magic happens when these vortices interact. Under extreme conditions like during a glitch, the vortices can suddenly pin to irregularities in the crust's nuclear lattice, creating a rotational traffic jam. Like cars piling up on a highway, pinned vortices store angular momentum until the tension becomes unbearable. Then, in a quantum avalanche, they unpin all at once, transferring a surge of momentum to the crust that astronomers detect as a sudden spin-up. This isn't just theory. Observations of glitches in pulsars like the Vela show precisely the two-stage recovery, an initial jump followed by a gradual adjustment that vortex unpinning predicts. Yet vortices might be responsible for even stranger behavior. Some neutron stars exhibit anti-glitches, a mysterious slowdowns where the star's rotation abruptly decreases. One explanation, vortices not pinned to the crust but to magnetic flux tubes in the superfluid. When these vortex bundles reorganize, they could briefly steal angular momentum from the star's rotation, like a figure skater extending their arms mid-spin. Other models suggest vortices might occasionally tangle like spaghetti in a pot, creating turbulent regions that sap energy through quantum friction, a phenomenon we've observed in lab superfluids, but scaled up to stellar proportions. The most tantalizing possibility is that these vortices could be telegraphing what's happening at the neutron star's core. If exotic particles like hyperons or free quakes exist there, their interactions with vortices would leave subtle fingerprints in the star's spin-down rate. Some theories even propose that vortex dynamics might explain why certain neutron stars emit fast radio bursts. Perhaps vortices snapping like rubber bands release energy that powers these cosmic fireworks. Every glitch, every hiccup in a neutron star's spin is a message written in the language of quantum whirlpools. By deciphering them, we're not just learning about distant stars, we're probing the limits of quantum mechanics itself, in conditions so extreme they turn textbook principles into cosmic scale mysteries. And with every new pulsar timing measurement, we get closer to answering a profound question. How do the rules of the infinitesimal shape the dance of the unimaginably vast? To truly understand how neutron stars spin, astronomers turn to two very different windows into the cosmos: X-rays and radio waves, each revealing secrets the other can't touch. X-ray telescopes catch the blistering glow of million-degree hotspots on a neutron star's surface, where magnetic fields funnel superheated particles into fiery columns. These bright patches act like cosmic beacons, rotating in and out of view as the star turns, allowing scientists to clock its spin with precision. But radio telescopes tell a different story. They detect the lighthouse like beams of pulsars, narrow jets of radiation powered by the star's whirling magnetic field. While X-rays show us the star's sizzling skin, radio waves let us eavesdrop on the precise metronome of its rotation, often with timing so exact it rivals atomic clocks. The synergy between these two wavelengths is where the magic happens. Take the case of a neutron star like Geminga, invisible to radio telescopes but blazing in X-rays. Here, X-ray hotspots revealed a spin rate of 4 times per second, solving a decades-old mystery about this silent spinner. Meanwhile, classic radio pulsars like the Crab often show glitches in their radio pulses before X-ray instruments spot corresponding surface heating, suggesting disturbances start deep inside the star before reaching the crust. It's like having both a stethoscope to listen to the star's heartbeat and a thermal camera to see its fever. But the real breakthrough comes when both signals align. Some neutron stars, like PSRJ 1023 plus 0038, switch between radio pulsar and X-ray binary states. In radio mode, their steady pulses trace the spin cleanly, but when they start accreting gas from a companion star, X-rays take over, showing how incoming matter scrambles the rotation. These transitional objects are cosmic Rosetta Stones, letting us decode how spin evolves under different conditions. And sometimes the two wavelengths outright disagree, like with magnetars, where X-rays reveal erratic spin changes while radio emissions when present stay rock steady. hinting at decoupled crust and core rotations. The next frontier, combining these observations with gravitational wave data. When X-rays and radio waves catch a neutron star mid-glitch, future detectors might sense the space-time ripples from its shuddering crust, giving us a 360-degree view of spin dynamics. Already, projects like NICER, an X-ray telescope mounted on the International Space Station, are mapping hotspot geometries to measure not just spin rates, but how warped the stars themselves are. Meanwhile, radio arrays like CHIME scan thousands of pulsars daily, creating a galactic-scale spin census. What makes this dual wavelength approach so powerful is how it mirrors the neutron star's own duality, a quantum core masked by a classical crust, a cosmic gyroscope wrapped in a magnetic storm. By listening to both its X-ray heartbeat and radio pulse, we're not just measuring spin, we're learning how the universe stitches together the infinitesimal and the infinite, one rotation at a time. For every neutron star that suddenly spins faster in a glitch, there's a rare rebel that does the opposite, slamming the brakes without warning. These anti-glitches are the universe's way of keeping astrophysicists humble, defying the neat explanations we've crafted for their speed-up cousins. Take the case of Magnetar 1e 1058.69, a neutron star with a magnetic field so strong it could strip data from a hard drive halfway to Pluto. In 2012, this cosmic oddball didn't just slow down, it shed rotational energy equivalent to 1 trillion atomic bombs in less than a minute, all without a visible explosion. What makes these events so baffling isn't just their rarity, it's that they flip the script on everything we think we know about neutron star interiors. Traditional glitches happen when the superfluid core's pent-up momentum surges into the crust, like a wound-up spring suddenly releasing. But anti-glitches suggest something far stranger, moments when the crust loses its grip on the core entirely. One leading theory points to the star's magnetic field rearranging itself like a tangled slinky suddenly snapping straight. When these field lines reorganize, they could transfer angular momentum outward, flinging energy into space instead of feeding it to the crust. Another possibility involves the superfluid's quantum vortices, those microscopic whirlpools normally responsible for spin-ups suddenly becoming chaotic. If vortices in the core abruptly unpin from the crust and swarm outward like bees abandoning a hive, they might carry rotational energy away from the star's surface. Or perhaps pockets of the superfluid briefly form a counter-rotating layer, creating internal friction where none should exist in a perfect quantum fluid. The most tantalizing clue comes from how these events unfold. Unlike glitches, which often show a quick jump followed by gradual recovery, anti-glitches sometimes exhibit a slow precursor, a slight wobble in the star's spin before the sudden slowdown. This hints at a buildup of stress deep inside, like tectonic plates shifting before an earthquake. Some magnetars even show X-ray flares coinciding with anti-glitches, suggesting magnetic upheavals might trigger both phenomena. What's at stake here isn't just academic curiosity. Anti-glitches could be telegraphing the existence of exotic states of matter in neutron star cores, phases where neutrons break down into quark-gluon plasma or hyperions. If the core's viscosity changes abruptly due to such a phase transition, it might temporarily couple to the crust differently, stealing spin energy instead of donating it. Every anti-glitch we detect is a cosmic knock on the door of our models, reminding us that neutron stars are more than just spinning tops. They're dynamic, layered worlds where quantum rules and relativistic forces collide in ways we're only beginning to decipher. And with each puzzling slowdown, the universe whispers a challenge: keep looking deeper. Some neutron stars don't just spin, they keep time better than the most advanced atomic clocks on Earth. Take PSR J0437-4715, a pulsar so steady its pulses arrive with a precision measured in nanoseconds over decades. This isn't just cosmic trivia. These spinning stellar remnants are rewriting the rules of navigation and physics, offering a celestial GPS system that could guide spacecraft between stars. The secret lies in their metronomic pulses. Unlike human-made clocks, which drift over time, millisecond pulsars maintain their rhythm through sheer cosmic inertia. Their incredible density, packing more mass than the Sun into a sphere the size of Manhattan, creates a flywheel effect so stable that even after thousands of years, their spin rates change by less than a second. Scientists realized this regularity could be harnessed as early as the 1970s, when radio telescopes first detected pulsars with timing precise enough to rival laboratory standards. But the real breakthrough came when researchers noticed subtle variations in these pulses, not from the stars themselves, but from the fabric of space-time they travel through. As gravitational waves ripple across the galaxy, they compress and stretch the space between Earth and distant pulsars, causing their signals to arrive a fraction of a second early or late. By monitoring networks of these cosmic clocks arrays like the European Pulsar Timing Array tracking over 60 pulsars, scientists have created a galaxy-scale gravitational wave detector. These arrays are so sensitive they could soon hear the background hum of supermassive black holes merging across the universe. Meanwhile, spacecraft engineers are putting pulsars to practical use. In 2016, NASA's Sextant experiment proved a pulsar-based navigation system could pinpoint the International Space Station's position to within 5 kilometers using only X-ray photons from distant neutron stars as guides. Unlike Earth-based systems that weaken with distance, pulsar navigation works anywhere in the galaxy, beaming time signals detectable for thousands of light years. Future interstellar probes could carry compact X-ray telescopes to triangulate their position by comparing pulses from multiple neutron stars, creating a Milky Way positioning system independent of Earth. What makes pulsar timing truly revolutionary is how it bridges quantum physics and cosmic scales. The same quantum effects that stabilize neutron spins in labs also govern these stellar clocks, while their immense gravity warps spacetime enough to test general relativity in extreme environments. Some pulsars, like the double pulsar system PSR J0737-3039, have provided the most stringent tests of Einstein's theories to date. Their orbital decay matching predicted gravitational wave energy lost to within 0.05%. Yet challenges remain. Interstellar gas scatters radio pulses, creating timing noise that must be painstakingly corrected. Some pulsars exhibit mysterious, red noise, slow, unexplained timing variations that could hint at undiscovered physics. And as we rely on these cosmic clocks for deeper tests of relativity, we're forced to confront an unsettling question. What if the constants of nature aren't so constant? Pulsar timing could reveal whether fundamental forces change over cosmic time, probing whether the universe's rules themselves are written in stone or etched in spinning stardust. The next time you glance at your phone's clock, consider this. The most accurate timekeepers in existence might not be in laboratories or satellites, but in the distant corpses of exploded stars, their rotations so unwavering they've become the heartbeat of the cosmos itself. And as we learn to read them more precisely, we're not just telling time, we're listening to the universe's deepest rhythms. Could invisible matter be secretly tugging at the universe's fastest spinners? Among the wildest theories in astrophysics is the idea that dark matter, the mysterious substance making up most of the universe's mass, might be meddling with neutron stars' rotations. Picture this as a neutron star plows through the Milky Way. It could act like a cosmic vacuum cleaner, sucking up dark matter particles that get trapped by its overwhelming gravity. Over millennia, these accumulated particles might sink to the star's core, subtly changing how mass is distributed inside. Since rotation depends on how mass is arranged, even a tiny imbalance could lead to measurable speed changes, like an ice skater pulling their arms in, but with invisible hands doing the adjusting. The math behind this is as fascinating as it is speculative. Dark matter particles, if they interact weakly with normal matter as most models suggest, would rarely collide with neutrons in the star. But given enough time, millions of years, even rare interactions could build up. Some simulations suggest a neutron star might capture enough dark matter to form a dense inner core, separate from the ordinary neutron fluid. This core could oscillate or slosh around, creating friction-like effects that drain rotational energy. Other models propose that certain types of dark matter particles could annihilate upon contact, releasing energy that heats the star's interior and alters its spin dynamics. Hints of this might already exist in the data. A handful of neutron stars like Pulsar B 1931+24 exhibit bizarre on/off behavior, alternating between pulsing normally and going radio silent for years. While conventional explanations point to magnetic field shifts, a few researchers speculate these pauses could align with dark matter clumps passing through the star, temporarily disrupting its rotation. Even more intriguing are isolated neutron stars spinning slower than expected, as if something invisible is applying the brakes. The challenge, dark matter's ghostly nature, makes it notoriously hard to pin down. Unlike magnetic fields or superfluid vortices, dark matter interactions wouldn't leave obvious X-ray or radio fingerprints, but upcoming gravitational wave observatories might change the game. If dark matter truly alters neutron star spins, the resulting gravitational waves could carry subtle imprints of these interactions, like hearing the distant echo of invisible fingers plucking a cosmic guitar string. Until then, this idea remains at the edge of known physics, a tantalizing what if that reminds us how much we still don't understand about the universe's hidden scaffolding. Whether dark matter truly influences neutron stars or not, the mere possibility stretches our imagination, forcing us to consider that the cosmos might be even stranger than its fastest spinning objects suggest. Deep inside a neutron star's core, where pressures crush atoms into a sea of neutrons, the rules of quantum mechanics don't just apply, they dominate in ways that defy intuition. Here, particles aren't just packed together, they might become quantum entangled, their fates intertwined across distances smaller than an atom, yet with effects that could ripple through the entire star. Imagine two dice rolled on opposite sides of the universe, always landing on matching numbers. That's the level of spooky connection we're talking about, but scaled up to trillions upon trillions of particles. This entanglement isn't just a curiosity. It could be the hidden force shaping how neutron stars spin, glitch, and even emit gravitational waves. Take the star's superfluid core, a realm where neutrons flow without friction. In ordinary fluids, viscosity slows motion, but here, quantum entanglement might synchronize particles so perfectly that they act as a single, coordinated entity. This could explain why some neutron stars rotate with such eerie stability, their spins locked in place like gears in a cosmic clock. When a glitch occurs, it might not just be vortices unpinning, it could be clusters of entangled particles suddenly decoupling, transferring momentum in quantum leaps rather than smooth transitions. The wildest possibility, entanglement might span the entire star. If particles in the core are linked to those near the crust, changes in one region could instantaneously affect another, bypassing the usual delays of physical forces. This could explain why some neutron stars recover from glitches in two distinct phases, an immediate jump followed by a gradual adjustment, as if the star's rotation is being negotiated between quantum factions. Yet proving this isn't easy. On Earth, quantum entanglement is fragile, collapsing at the slightest disturbance. But inside a neutron star, gravity's crushing embrace might stabilize these connections, creating a macroscopic quantum system unlike anything we've observed. Some theorists even speculate that entangled states could generate subtle gravitational anomalies, leaving fingerprints in the star's gravitational wave emissions. While we can't peer directly into these dense cores, pulsar timing might hold clues. If entanglement influences spin, carefully mapped glitches could reveal patterns, like a preferred quantum rhythm in how rotational energy redistributes. Future gravitational wave detectors, sensitive enough to catch vibrations from individual neutron stars, might someday pick up the faint hum of entangled particles rearranging themselves. This isn't just physics, it's a cosmic test of quantum mechanics pushed to its absolute limit. If entanglement truly governs neutron star spins, it would mean the universe's most massive quantum systems are hiding in plain sight, spinning silently in the dark. And with every pulse, every glitch, they're sending us encrypted messages about the fundamental nature of reality itself. Some neutron stars spin with such strange, erratic rhythms that they seem to be ticking to the beat of an entirely different universe. Take PSR J090 1-4046, a recently discovered pulsar that emits radio bursts at intervals ranging from mere seconds to several minutes. No known physics can fully explain its bizarre cadence. These cosmic outliers aren't just oddities, they're potential treasure maps pointing toward physics beyond our wildest theories. Could their irregular spins be the fingerprints of exotic particles like actions or sterile neutrinos, particles so elusive they've never been detected on Earth? Or might their rotations reveal hidden dimensions, warping spacetime in ways Einstein never envisioned? One tantalizing clue lies in how certain neutron stars lose rotational energy. While most pulsars slow down predictably as their magnetic fields radiate energy into space, a few, like the Black Widow pulsar PSRB 1957 +20, decelerate faster than any model predicts. This excess braking can't be explained by traditional electromagnetism alone. Some theorists propose these stars are shedding energy by emitting not just photons, but hypothetical particles like gravitons or dark matter candidates, carrying away angular momentum invisible to our telescopes. Others suggest their magnetic fields might be tapping into quantum foam, the frothy, subatomic texture of spacetime predicted by quantum gravity theories. Then there's the enigma of slow-spin neutron stars. Conventional astrophysics says these objects should spin at least once every few seconds, yet objects like 1e 161,348 -5055 in the supernova remnant RCW 103 rotate once every 6.5 hours slower than a record player at its lowest setting. One radical explanation: these stars might harbor quark nuggets in their cores, ultra-dense blobs of free quarks that sap rotational energy through frictionless quantum drag. Alternatively, their spin could be impeded by cosmic strings, hypothetical, spaghetti-like defects in spacetime left over from the Big Bang, wrapping around the star like invisible anchor lines. The most mind-bending possibility involves extra dimensions. String theory suggests our universe might have hidden spatial dimensions curled up at microscopic scales. Near a neutron star's crushing gravity, these dimensions could unfurl, subtly altering how rotation propagates through spacetime. If true, a neutron star's spin-down rate could carry encoded signatures of these dimensions, like a cosmic phonograph needle vibrating to the shape of unseen grooves. What makes these mysteries so urgent is how they bridge the infinitesimal and the cosmic. A single neutron star's spin anomaly could upend decades of particle physics, offering clues to unification theories that laboratories like CERN can't yet probe. Every unexplained glitch, every erratic pulse, is a potential Rosetta Stone, a cipher waiting to be cracked. And with next-generation telescopes like the Square Kilometre Array coming online, we're on the verge of listening to these cosmic spin doctors like never before, tuning our instruments to the whispers of a universe far stranger than we've dared to dream. Peering into the heart of a neutron star requires more than telescopes. It demands the raw computational power of supercomputers crunching numbers at speeds rivaling the stars themselves. These virtual laboratories recreate conditions impossible to study on Earth, simulating densities where a single sugar cube's worth of material would outweigh Mount Everest. One groundbreaking simulation from the Oak Ridge National Laboratory used over 20 million CPU hours to model just 1 millisecond of a neutron star's life, tracking trillions of particle interactions in a quantum dance. What emerged wasn't just data, it was a revelation. The simulations showed how superfluid vortices, those microscopic whirlpools in the star's core, don't just move randomly. They snap into orderly lattices like iron filings aligning to a magnet, channeling angular momentum with eerie precision. Yet the real surprise came when researchers tweaked the magnetic fields. In some models, magnetic threads became tangled like spaghetti in a cosmic blender, creating pockets of resistance that triggered sudden spin changes. Other simulations revealed how crustquakes might propagate not as simple fractures, but as cascading failures where one cracking crystal nucleus sets off a chain reaction across the entire star. These virtual experiments even reproduced glitches with startling accuracy, showing how vortex avalanches in the superfluid could explain why some neutron stars speed up without warning. But perhaps the most haunting discovery was how these simulations exposed gaps in our theories. When scientists at the University of Illinois tried to simulate a magnetar's interior, their model predicted magnetic fields should tear the star apart within centuries, yet real magnetars persist for millennia. This discrepancy hints at unknown stabilizing forces, possibly from exotic particles or quantum entanglement effects we've yet to account for. Other teams have found that including quark matter cores in their simulations leads to spin behaviors matching those odd, slow rotators observed in deep space surveys. The frontier now lies in coupling these models with gravitational wave predictions. Advanced simulations at MIT suggest that certain spin frequencies should produce resonant vibrations in spacetime, subtle tremors future detectors like LISA might catch. Already, these digital neutron stars are becoming Rosetta Stones, translating the language of quantum mechanics into the macro-scale drama of spinning stellar corpses. And as supercomputers grow more powerful, we're not just simulating stars, we're unraveling the universe's most extreme physics, one virtual revolution at a time. Among the cosmos's most ruthless predators lurk the Black Widow pulsars, neutron stars that didn't just outlive their stellar companions but are actively devouring them. These systems aren't just morbid curiosities. They're cosmic laboratories where gravity, magnetism, and rotation collide in extreme ways. Take PSRB 1957 plus 20, the original Black Widow, spinning 622 times per second while its faint companion star, now whittled down to a fraction of its original mass, endures relentless blasts of radiation. The pulsar's beams act like a blowtorch, slowly vaporizing the companion's outer layers, while its gravity strips away material in a swirling stream, a process that unpredictably tugs on the pulsar's own rotation like a yo-yo on an invisible string. What makes these systems so unstable is the delicate balance between consumption and spin. As the pulsar siphons gas from its doomed partner, the incoming matter carries angular momentum, which should theoretically speed up the pulsar's rotation. But reality is messier. Some black widows like Pulsar J 1311-3430 show sudden, erratic spin downs instead, moments where the star slows abruptly, as if hitting an invisible wall. The culprit, torque reversals, where the flow of stolen matter temporarily backfires. If the companion star's vapor forms a disk around the pulsar that briefly flips orientation, it can transfer momentum in the opposite direction, applying electromagnetic brakes to the pulsar's spin. Even stranger are the redback pulsar's black widow cousins, where the companion star hasn't yet been fully evaporated. These systems, like Pulsar J 1023+0038, alternate between two states, a quiet radio pulsar mode and a violent X-ray emitting phase when gas from the companion overwhelms the pulsar's magnetic field, burying its beams under an avalanche of plasma. Each switch flips the star's rotational dynamics. In radio mode, the pulsar spins down steadily, its magnetic field breaking the rotation like a paddle in water. But during X-ray outbursts, the infalling matter can temporarily accelerate the star, creating a seesaw effect that leaves astronomers scrambling to model the timing. The most bizarre cases are the black widows with planetary corpses. Pulsar J 1719-1438 orbits a companion so dense a crystallized carbon remnant that it's essentially a diamond the size of Jupiter. Here, the pulsar's rotation isn't just shaped by gas streams, but by tidal forces from this ultra-compact object, creating subtle, month-long wobbles in its spin. These systems hint that black widows might not always finish their meals. Sometimes they leave behind crystallized remnants, their gravitational whispers still tweaking the predator's rotation millennia later. What fascinates astrophysicists isn't just the violence of these systems, it's what they reveal about angular momentum's cosmic budget. Every erratic spin change, every torque reversal, is a ledger entry in how the universe redistributes rotation. Some black widows even challenge our understanding of the pulsar deathline, the theoretical spin threshold below which a neutron star's beams should flicker out. Yet Pulsar B 0943+10, a suspected black widow, pulses steadily despite spinning just once per second, suggesting these predators might rewrite the rules of how pulsars live and die. As we discover more of these cosmic spiders, often via the gamma-ray shadows they cast while vaporizing their companions, we're glimpsing a hidden chapter of stellar evolution. Not all neutron stars fade quietly. Some spin themselves into oblivion by feasting on the stars they once called neighbors. And with each erratic pulse, they remind us that in the cosmos, even rotation isn't just physics, it's survival. Neutron stars don't always spin alone. Some are locked in a gravitational tango with another star, and this cosmic partnership can turn an ordinary stellar remnant into a rotational powerhouse. Picture two dancers, one massive and dense, the other lighter and more fluid, whirling around each other in a celestial ballet that can last billions of years. As they orbit, the neutron star's immense gravity can strip material from its companion, pulling gas into a swirling disk of superheated plasma. But this isn't just a one-way theft, it's a transfer of momentum, where every stolen atom carries a tiny push that can speed up the neutron star's spin like a child on a merry-go-round catching tossed weights. These binary systems are cosmic gold mines for astrophysicists because they let us witness spin dynamics in real time. Take the famous X-ray binary system Centaurus X3, where a neutron star slurps gas from a supergiant companion, spinning up to nearly 200 rotations per second. The infalling matter doesn't just pile onto the surface, it's funneled along magnetic field lines, crashing onto the star's poles with enough force to create X-ray hotspots that pulse like a strobe light. By tracking these pulses, astronomers can measure the star's spin with millisecond precision, watching as it accelerates over months or years. But the real drama unfolds in systems with tighter orbits. In so-called ultra-compact X-ray binaries, the neutron star and its companion are so close they could fit inside our Sun, completing orbits in less than an hour. Here, the transfer of matter becomes a chaotic torrent, with gas spiraling inward at relativistic speeds. Sometimes, the neutron star's magnetic field resists this flow, creating a tug of war that produces sudden torque reversals moments when the star's spin slows unpredictably, as if hitting an invisible wall. Other times, the accumulated gas becomes unstable, triggering thermonuclear explosions on the neutron star's surface that release as much energy in seconds as the Sun does in weeks. The most extreme examples are the Black Widow and Redback pulsars, where the neutron star's radiation and particle winds actively erode its companion, leaving behind a ghostly husk. In these systems, the spin-up process is a double-edged sword. While accretion can rev the pulsar's rotation to blistering speeds, the evaporation of the companion star eventually shuts off the fuel supply, leaving the neutron star to spin down alone. It's a cosmic irony. The very mechanism that accelerates these stars also ensures their eventual slowdown. Yet binary systems don't just teach us about spin, they also reveal the universe's hidden reserves of angular momentum. In some cases, the companion star isn't a lightweight victim but another neutron star or even a black hole. When these heavyweights orbit each other, their mutual frame dragging twists spacetime into knots, emitting gravitational waves that carry away rotational energy. The famous Hulse-Taylor binary, a pair of neutron stars discovered in the 1970s, provided the first indirect proof of gravitational waves by showing how their orbit shrinks over time, exactly as Einstein's equations predict. What makes these partnerships so illuminating is how they blur the line between destruction and creation. A neutron star might steal matter to speed up, but that same process can forge heavy elements in the accretion disk's fiery crucible. It might rip its companion apart, but the debris could someday coalesce into new planets or even future stars. And when two neutron stars finally collide, their merger doesn't just end the dance, it sends ripples through spacetime and scatters gold across the cosmos. Every binary system is a chapter in a story where rotation isn't just physics, it's the rhythm of creation itself. The next decade promises to revolutionize our understanding of neutron star spins, with groundbreaking telescopes and detectors poised to peel back layers of mystery we've barely begun to explore. Imagine instruments so sensitive they could detect the slightest wobble in a pulsar's rotation from halfway across the galaxy, or catch the gravitational whispers of a single quantum vortex snapping inside a superfluid core. The Square Kilometre Array, set to begin observations in the late 2020s, will monitor thousands of pulsars simultaneously with unprecedented precision, creating a galactic-scale network of cosmic clocks. This pulsar timing array won't just track spin rates, it could uncover the fingerprints of passing gravitational waves from supermassive black hole mergers, warping spacetime as they ripple through the Milky Way. Meanwhile, next-generation gravitational wave observatories like the Einstein Telescope and LISA will open entirely new windows into neutron star dynamics. While current detectors like LIGO catch the violent collisions of these stellar remnants, future instruments will listen for subtler vibrations, the continuous hum of a lone neutron star's mountains deforming under extreme gravity, or the resonant tremors of a glitch propagating through its interior. Some theories predict that certain spin frequencies might excite R modes, oscillations in the star's fluid layers that emit gravitational waves strong enough to be detected across interstellar distances. If found, these signals could reveal whether neutron star cores contain free quarks or other exotic particles, effectively turning these stars into cosmic particle accelerators too extreme to replicate on Earth. X-ray astronomy is also leaping forward. Missions like ESA's Athena and NAS-A-Lynx will map hotspots on neutron star surfaces with resolution sharp enough to distinguish features smaller than a football field, allowing us to watch in real time as magnetic fields twist crustal plates or as accretion columns from companion stars slam into the surface, altering rotation. These observations might finally solve puzzles like why some neutron stars exhibit anti-glitches, or how magnetars sustain magnetic fields strong enough to briefly outshine the entire Milky Way. Perhaps the most tantalizing possibility lies in the unexpected. History shows that every time we've built telescopes with new capabilities, from radio arrays to gravitational wave detectors, we've discovered phenomena nobody predicted. Could there be neutron stars spinning faster than theory allows, held together by unknown quantum forces? Might we find objects transitioning between neutron stars and quark stars, their spins betraying the phase change? Or could some pulsar's erratic timing be caused not by internal dynamics, but by external factors like dark matter annihilation or even primordial black holes passing through them? The answers won't just rewrite textbooks, they'll redefine our place in the cosmos. Each precise measurement of a neutron star's spin is a direct test of general relativity and quantum mechanics in conditions so extreme they border on the surreal. And as these spinning beacons reveal their secrets, they'll illuminate everything from the birth of heavy elements to the fate of space-time itself. The universe has been running these experiments for billions of years. Now, at last, we're building the tools to read the results. Neutron stars don't just exist within space-time, they twist it, stretch it, and rewrite its rules with every rotation. These cosmic heavyweights pack so much mass into such a small volume that they dent the fabric of the universe like a bowling ball resting on a trampoline. But unlike a static dent, their rapid spins send ripples through spacetime itself, dragging it along in a swirling vortex known as frame dragging. Picture a spoon stirring honey. Just as the honey clings to the spoon and twists around it, spacetime clings to a spinning neutron star, warping into a dynamic, ever-changing shape that defies classical intuition. This isn't just theoretical, we've seen it in action. Take the binary system PSRJ 1141-6545, where a neutron star orbits a white dwarf. Over decades of observations, astronomers noticed the pulsar's orbit slowly tilting, as if nudged by an invisible hand. The culprit, frame dragging. As the neutron star spins, it yanks spacetime around with it, subtly altering the white dwarf's path in a way that perfectly matches Einstein's predictions. It's as if the universe itself is confirming relativity's most mind-bending consequences, using neutron stars as its chalkboard. But the real magic happens when quantum mechanics enters the mix. Deep inside a neutron star, where densities reach levels trillions of times greater than anything on Earth, the rules of the very small collide with the warping of spacetime on cosmic scales. Here, the star's superfluid core, a quantum mechanical marvel where neutrons flow without friction, interacts with the twisted spacetime around it in ways we're only beginning to understand. Some theories suggest that the vortices in this superfluid could align with the frame dragging effect, creating a feedback loop that stabilizes the star's spin over millennia. Others propose that these quantum whirlpools might occasionally tangle, releasing bursts of energy that ripple outward as gravitational waves. The implications stretch far beyond neutron stars themselves. Every time we measure how these objects warp spacetime, whether through pulsar timing, gravitational wave detection, or X-ray observations, we're stress-testing general relativity in conditions no lab could ever replicate. When the LIGO detector caught gravitational waves from colliding neutron stars in 2017, the signal didn't just reveal a cosmic collision. It showed how spacetime itself vibrated under the strain of merging ultra-dense objects, confirming that gravity travels at the speed of light to within 1 part in a quadrillion. Yet mysteries remain. Why do some neutron stars exhibit frame-dragging effects stronger than predicted? Could exotic states of matter in their cores like quark-gluon plasma or free quarks amplify spacetime warping in unexpected ways? And what happens when a magnet's unimaginably strong magnetic field, capable of bending atoms into needles, interacts with the twisted spacetime around it? Each observation peels back another layer, revealing a universe where the fabric of reality is far more malleable and far stranger than we ever imagined. The beauty of these cosmic laboratories is how they bridge the vast and the infinitesimal. A single neutron star's spin can teach us about the quantum behavior of particles smaller than atoms, while simultaneously probing the structure of spacetime across light years. And as our tools grow sharper, from next-generation gravitational wave detectors to space-based X-ray telescopes, we're not just watching these stars warp the universe. We're learning to read the wrinkles they leave behind, one rotation at a time. At the very heart of a neutron star, where pressures exceed 100 trillion times Earth's atmosphere, ordinary matter doesn't just get squeezed, it might unravel into something far stranger. Forget neutrons. Here, the building blocks of protons and neutrons themselves, quarks, could break free from their usual confines, swimming in a primordial soup known as quark matter. This isn't just theoretical speculation. When you pack so much mass into a space smaller than Manhattan, the rules of nuclear physics start to bend. Under these conditions, quarks, normally shackled together by the strong force, might finally snap their chains, creating a fluid so dense it makes the core of an atom look like empty space. The implications for spin are profound. A neutron star with a quark core wouldn't just rotate, it would whirl with a different kind of frictionless efficiency. Unlike ordinary neutron fluid, where vortices govern momentum transfer, quark matter could flow with even less resistance, potentially explaining why some pulsars glitch more violently than others. Picture two skaters spinning on ice, one on smooth, liquid-like quark matter, the other on the slushier neutron superfluid. The quark skater would pirouette with eerie stability, while the neutron skater might stumble occasionally as vortices pin and unpin. This could explain why certain neutron stars, like the Vela pulsar, exhibit glitches with textbook-perfect vortex unpinning signatures, while others, like the enigmatic PSR J0537-6910, show erratic spin-ups that defy conventional models. Observational hints of quark matter are tantalizing but elusive. One clue comes from the mass-radius relation. Neutron stars with quark cores should squish differently under gravity's grip. Their maximum possible mass might be slightly lower, or their surfaces slightly more deformable. When NICER telescope mapped the size of pulsar J0030 plus 0451, it found a star both lighter and fluffier than some quark star models predicted, leaving the door open for exotic cores. Even more compelling are gravitational wave signals from neutron star mergers. In 2017, LIGO detection of two colliding neutron stars revealed a post-merger remnant that lingered just a few milliseconds before collapsing into a black hole, a delay some theorists argue could only happen if the stars had quark cores stiff enough to briefly resist gravitational doom. Yet skeptics point to gaps in the evidence. If quark matter exists, why don't all neutron stars above a certain mass show identical spin behaviors? Why do some pulsars with similar masses glitch while others don't? The answer might lie in a cosmic gradient. Stars with the highest densities could harbor quark cores, while slightly lighter ones remain traditional neutron stars. Or perhaps quark matter isn't uniform. It could form intricate layers like an onion with a quark core wrapped in a neutron mantle, each layer spinning at slightly different rates. The hunt for quark matter isn't just about rewriting astrophysics textbooks, it's a window into the universe's most extreme states of matter, conditions that existed microseconds after the Big Bang and nowhere else today. If future gravitational wave detectors catch a neutron star vibrating at frequencies only possible with a quark core, or if telescopes spot a pulsar whose spin-down pattern matches quark matter simulations, we'll have more than just a new celestial curiosity. We'll have proof that nature permits a substance so exotic, it blurs the line between star and particle accelerator, a place where the universe's tiniest components dictate the dance of its densest objects. Deep inside a neutron star's ultra-dense crust, where pressures could flatten mountains into sheets thinner than paper, the ground doesn't just crack, it sings. These aren't the silent fractures of Earth's earthquakes, but resonant vibrations that ripple through the star's entire structure, sending oscillations ringing through spacetime itself. Scientists call them starquakes, and the frequencies they produce, some as low as a foghorn's drone, others higher than a piano's top note, carry encrypted messages about what's happening beneath the surface. Imagine tapping a crystal glass and listening to its ring to deduce whether it's filled with water, sand, or mercury. Now scale that up to a stellar corpse with the mass of a sun, and you've got the essence of neutron star seismology. The most revealing oscillations come from abrupt crustal shifts. When a neutron star's rigid outer layer, a lattice of atomic nuclei packed tighter than sardines, suddenly yields to stress, it can fracture like a diamond under a hammer blow. These starquakes release energy equivalent to a magnitude 32 earthquake, but what's astonishing isn't the power, it's the aftermath. The crust doesn't just break, it vibrates at precise frequencies determined by the star's density, magnetic field, and internal composition. Some oscillations resemble the standing waves in a wineglass, while others spiral through the star like the harmonics of a tuning fork struck in zero gravity. Detecting these cosmic sound waves isn't about listening with microphones, it's about precision timing. When a starquake rattles a pulsar, its lighthouse-like radio beams can flicker in sync with the vibrations, like a wobbly record needle distorting a song. The Rossi X-ray Timing Explorer satellite caught one such event in 2004 from Magnetar SGR 1806-20, recording oscillations at 94 Hz, a frequency that would sit just below a tuba's lowest note. By analyzing these tremors, researchers realized the star's crust must be 10 billion times stronger than steel to vibrate that way, rewriting models of neutron star surfaces. But the real goldmine lies in what these frequencies reveal about the interior. Just as geologists use seismic waves to map Earth's core, astrophysicists can invert oscillation patterns to probe a neutron star's hidden layers. A sudden drop in frequency might betray the boundary where the solid crust gives way to the superfluid ocean beneath, while harmonic overtones could hint at the core's exotic contents, whether quark matter, hyperons, or other states unknown on Earth. Some theories even suggest that certain oscillation modes might only exist if the core resembles an enormous atomic nucleus, blurring the line between star and particle. Yet the most tantalizing vibrations are those we haven't heard yet. Simulations predict that torsional oscillations, twisting motions in the crust, could couple with magnetic fields to produce detectable gravitational waves, especially in magnetars where fields are strong enough to distort spacetime on their own. Future observatories like the Einstein telescope might catch these spacetime ripples, effectively turning neutron stars into cosmic bells whose rings reveal their inner structure across interstellar distances. Every starquake is more than a celestial curiosity. It's a backstage pass to physics at the edge of impossibility. From the pitch of these oscillations, we can estimate a neutron star's temperature, the thickness of its crust, even the viscosity of its superfluid heart. And with each new vibration detected, we're one step closer to answering the ultimate question: what happens to matter when gravity strips it down to its most fundamental essence? The universe isn't just showing us these stars, it's letting us hear them, one cosmic note at a time. Neutron stars don't just spin, they're cosmic particle accelerators, wielding magnetic fields trillions of times stronger than Earth's to sling charged particles to nearly the speed of light. These aren't gentle nudges, they're violent, relativistic launches that transform the space around the star into a high-energy physics lab. Picture a cosmic slingshot. As particles like electrons and protons get caught in the star's magnetic grip, they spiral along field lines with such force that they emit radiation across the spectrum, from radio waves to gamma rays, creating brilliant auroras that could outshine entire galaxies. But this isn't just a light show. The energy these particles carry directly tugs on the star's rotation, like a rocket engine firing in reverse, gradually bleeding away its spin over millennia. The mechanics behind this are as mesmerizing as they are complex. Near the magnetic poles, where field lines converge like a funnel, particles are accelerated so violently that they generate beams of X-rays and gamma rays, the same pulses we detect as pulsars. But these beams don't just stream outward harmlessly. They interact with the star's magnetosphere, a turbulent zone of plasma and twisted magnetic fields, creating drag that acts like an interstellar brake. This magnetic braking is why young pulsars, fresh from supernova and bristling with energy, slow down dramatically within their first 100,000 years, while older, more sedate neutron stars barely lose a rotation per century. Yet some neutron stars defy this pattern. Magnetars, for instance, exhibit erratic spin-down rates despite their colossal magnetic fields. Here, the rules change. Their fields are so strong, 1,000 times more intense than typical pulsars, that they can fracture the star's crust in starquakes, releasing bursts of energy that momentarily overpower the braking effect. Even stranger are the wind nebulae around some pulsars, like the Crab Nebula's beating heart. The particles accelerated by the central neutron star collide with surrounding gas, creating shock waves that glow across the electromagnetic spectrum. These nebulae aren't just byproducts, they're cosmic feedback loops where the energy lost to particle acceleration shapes the environment that, in turn, influences the star's spin. The most extreme cases blur the line between particle physics and astrophysics. In Black Widow pulsars, the radiation and particle winds are so intense they vaporize nearby companion stars, creating a feedback loop where the star's own acceleration mechanisms erode the very source of material that could alter its rotation. Meanwhile, theorists speculate that certain high-energy particles might escape the magnetosphere entirely, becoming ultra-high-energy cosmic rays, the same mysterious particles that occasionally slam into Earth's atmosphere with energies rivaling a baseball pitch. What ties all this together is the delicate balance between creation and dissipation. Every particle accelerated to near light speed carries away a whisper of the star's angular momentum, a trade-off between radiative brilliance and rotational decay. It's a reminder that neutron stars aren't just inert relics, they're dynamic engines, their spins etched into the high-energy signatures they broadcast across the cosmos. And with each pulse, each burst of radiation, they reveal how the universe transforms rotation into light, and light into the fundamental particles that shape everything we see. Spin isn't just a feature of a neutron star's life, it's the clock ticking down to its eventual fate. Over billions of years, even the fastest pulsars gradually lose their rotational energy, their beams dimming as the universe siphons away their momentum. But this slowdown isn't just a quiet fade to black. Depending on how a neutron star spins and, more importantly, how it slows, its final act could range from a whisper to a cataclysm. Take the quietest endings first. Some neutron stars, particularly those born with weaker magnetic fields or in isolation, spin down so gently they become nearly undetectable. Like a top winding to a stop on a frictionless table, these stars gradually lose their lighthouse beams, their radio pulses growing fainter until they vanish entirely. But even in silence, they're not truly dead. Their cores remain searingly hot, their surfaces still dotted with magnetic hotspots that glow faintly in X-rays. Given enough time, trillions of years, far longer than the current age of the universe, these cold remnants would crystallize entirely, becoming celestial diamonds adrift in the darkness. But not all neutron stars get to retire peacefully. For those born with extreme mass or those that gain too much matter from a companion star, spin plays a cruel trick. As they slow, the outward centrifugal force that once helped counteract gravity weakens, allowing the star's own weight to press inward. For most, this is a non-issue. Their incredible density keeps them stable. But cross a critical threshold and the star's core succumbs. The exact moment of collapse depends on a delicate balance. The star's mass, its equation of state, a fancy term for how matter behaves under such extremes, and yes, its spin. A rapidly rotating neutron star can stave off collapse longer than a slow spinning one, its rotation propping it up like a cosmic merry-go-round fighting gravity's pull. The most dramatic collapses happen in binary systems. When a neutron star feasts on a companion, it can gain enough mass to tip the scales. But here's the twist: accretion doesn't just add weight, it often speeds up the star's spin, temporarily delaying the inevitable. This sets up a race against time. Can the star shed enough angular momentum through magnetic braking or gravitational waves before it becomes too heavy? Sometimes the answer is no. Simulations show that when these stars finally buckle, it's not a smooth transition. The core collapses first, forming a black hole, while the outer layers, still spinning rapidly, briefly form a whirling disk before being swallowed. The result, a gamma-ray burst, one of the universe's most violent explosions, powered by the last desperate revolutions of a dying star. Then there are the middle paths neutron stars that don't quite collapse but transform. Some theorists suggest that as certain neutron stars spin down, their cores might undergo a phase transition, with neutrons dissolving into a soup of free quarks. These quark stars could exist in a precarious state, their spin rates subtly different from ordinary neutron stars, their gravitational waves ringing with unique frequencies. Others speculate that ultra-slow rotators might develop strange new states of matter, like superconducting cores or Bose-Einstein condensates, which could leave detectable imprints in their cooling curves. What makes these endings so fascinating is how they link spin to the universe's grand cycles. A neutron star's rotation isn't just a number, It's a ledger of its history and a predictor of its future. The gold in your jewelry, the cosmic rays hitting our atmosphere, even the gravitational waves humming through space, many of these trace back to neutron stars and how they spun their way toward oblivion. And with every new observation, we're piecing together the final chapters of these stellar stories, one rotation at a time. Hollywood loves neutron stars for their dramatic potential, cosmic mavericks capable of warping time, crushing spaceships, or powering alien civilizations. But strip away the special effects, and how many sci-fi tropes hold up to real astrophysics? Take Christopher Nolan's Interstellar, where the crew visits a planet orbiting a spinning neutron star. The film nails the time dilation effect, where gravity slows time near the star but cranks it up to implausible extremes. In reality, you'd need to orbit dangerously close to experience even a fraction of that time warp, and tidal forces would shred any planet long before it became habitable. Then there's Star Trek, where neutron stars often serve as navigational hazards or energy sources. While their intense gravity makes them plausible cosmic roadblocks, the idea of harvesting their energy ignores a critical hurdle: the sheer lethality of their radiation. A starship venturing near a pulsar's beam would be bombarded with X-rays and gamma rays powerful enough to vaporize its hull in seconds. No shields could withstand that. Even The Expanse, praised for its hard sci-fi realism, takes liberties with the Rocinante's close encounter with a neutron star's jet. In truth, those particle streams travel near light speed. A ship wouldn't just shake it, it'd be atomized. Yet some fictional depictions get eerie details right. Event Horizon's derelict ship orbiting a pulsar. The concept of a dead neutron star radiating residual heat aligns with real science. And Doctor Who's The Impossible Planet episode cleverly imagines a civilization living on a planet locked in a neutron star's gravity well, though the writers wisely avoid explaining how anything survives the crushing pressure and lethal magnetic fields. The gap between fiction and reality isn't just about accuracy, it's about scale. Movies often portray neutron stars as looming visually in space, but in truth, even the largest would appear as tiny pinpricks from a safe distance. Their real terror lies in their invisible forces, gravitational waves that could destabilize orbits light years away, or magnetic fields so strong they'd scramble a ship's electronics before it even got close. Where sci-fi truly misses the mark is in portraying neutron stars as static set pieces. Real neutron stars are dynamic. Pulsars slow down, magnetars erupt without warning, and binary systems spiral toward cataclysmic mergers. A film capturing their true nature would be less about explosive visuals and more about the slow, inexorable physics governing their spin and decay. Perhaps the most striking difference is longevity. Fictional neutron stars often exist as eternal backdrops, but real ones evolve. Over billions of years, their rotations wind down, their magnetic fields fade, and their brilliant beams flicker out. The universe doesn't need melodrama to make these objects fascinating. Their genuine physics, from quantum vortices to space-time warping, is stranger than any script. And that's the real irony. The truth about neutron stars is so extraordinary, it doesn't need Hollywood's embellishment to captivate us. Peering into the heart of a spinning neutron star used to be pure imagination, until scientists built virtual laboratories where these cosmic powerhouses come to life in stunning detail. Picture a 3D simulation so precise it captures individual vortices swirling in the superfluid core, each one a microscopic whirlpool influencing the star's rotation. These aren't just pretty visuals, they're mathematical masterpieces, crunching equations that account for everything from quantum entanglement in the core to relativistic frame dragging at the surface. One groundbreaking model from the University of Illinois simulates a neutron star's spin down to the femtosecond, revealing how magnetic field lines snap and reconnect like cosmic rubber bands, unleashing bursts of energy that alter its rotation in real time. What makes these tools revolutionary is how they translate abstract physics into tangible motion. Take the crust crack simulation, where researchers at Caltech modeled a starquake rippling through a neutron star's rigid outer layer. As the crust fractures, the entire star shudders, sending gravitational waves pulsing outward, an event mirrored in actual observations of magnetars. Or consider the vortex avalanche visualization, which shows how quantum whirlpools in the superfluid core can suddenly unpin from the crust, transferring momentum so violently that the star's spin jumps in a glitch. These simulations don't just match theory to observation. They've predicted behaviors later spotted in real pulsars, like the two-stage recovery of the Vela pulsar's famous glitches. For the public, these models become gateways to understanding. NASA Neutron Star Mission Interactive lets users tweak a star's mass, spin, and magnetic field, then watch as its lighthouse beams and crustal stresses evolve in real time. The European Space Agency's Pulsar Playground even simulates how frame dragging warps space-time around a rapidly rotating star, creating a visible distortion that mimics a cosmic vortex. These tools demystify concepts like superfluidity, showing how a neutron star's core flows with zero friction, like a perfectly stirred cup of quantum coffee that never stops spinning. Yet the real magic happens when simulations collide with real data. When LIGO detected gravitational waves from colliding neutron stars in 2017, supercomputer models had already mapped thousands of possible merger outcomes. By comparing these virtual scenarios to the actual event, scientists decoded the star's internal structure from their final, frenzied orbits. Similarly, X-ray pulse profiles from NICER observations of pulsar J0030 plus 0451 were matched against millions of simulated hotspot configurations, revealing the star's surface topography with unprecedented precision. The future of these virtual explorers is even brighter. Upcoming exascale computers will simulate entire magnetospheres at resolutions fine enough to track individual particle collisions, while machine learning algorithms could soon predict glitches before telescopes spot them. For scientists, these models are proving grounds for wild theories like quark-nova explosions or spacetime warping mountains on neutron star surfaces. For the rest of us, they're a front-row seat to the universe's most extreme physics, where the invisible forces shaping neutron stars finally step into the light. From their bizarre quantum cores to their relativistic spins, neutron stars continue to defy expectations, challenging everything we thought we knew about the universe. These cosmic enigmas are more than just stellar remnants. They're living laboratories where the laws of quantum mechanics and gravity collide on a scale we can barely comprehend. Every flicker of a pulsar's beam, every sudden glitch in rotation, and every ripple of gravitational waves carries a message, a clue to the fundamental nature of matter and spacetime itself. Take something as seemingly simple as a neutron star's spin. On the surface, it's just rotation, but dig deeper, and you'll find a symphony of forces at play. The superfluid vortices swirling in its core, the crust cracking under unimaginable strain, the magnetic fields twisting spacetime like taffy. All of these elements intertwine to create a celestial clockwork so precise, it rivals our best atomic timekeepers. Yet, even with all we've learned, these stars keep surprising us. Why do some suddenly slow down instead of speeding up? What causes the mysterious red noise in their timing? Could dark matter be subtly tugging at their spins? Each unanswered question is a doorway to new physics, a reminder that the universe is far stranger than we've dared to imagine. The beauty of neutron stars lies in their duality. They're both impossibly dense and incredibly dynamic, governed by the tiniest quantum rules, yet shaping the cosmos on a grand scale. When two neutron stars merge, they don't just vanish, they scatter gold across the galaxy, seed new stars, and send gravitational waves echoing through the fabric of spacetime. Their spins are more than just motion. They're a record of cosmic history, a ledger of how matter behaves under the most extreme conditions nature can muster. As technology advances, so too will our ability to decode these stellar puzzles. Next-generation telescopes, gravitational wave detectors, and supercomputer simulations are peeling back layers of mystery faster than ever before. We're on the verge of hearing the hum of a single neutron star's vibrations, mapping the quantum turbulence in its core, and perhaps even glimpsing the elusive quark matter that might lurk within. Every discovery doesn't just answer old questions, it sparks new ones, pushing the boundaries of what we thought was possible. So what other secrets might these incredible objects hold? Could they harbor exotic states of matter we've never seen? Might their spins reveal hidden dimensions or new fundamental particles? The only way to find out is to keep looking, to stay curious, and to let these cosmic marvels guide us deeper into the unknown. After all, the universe has been running these experiments for billions of years. Now it's our turn to listen